Good day, viewers, and welcome to our today's class. For today, we are going to be dealing with thermodynamic relation. The question on the board says, for a perfect gas obeying PV is equals to RT, we should show that CV and Cp are independent of pressure. So now, we know that we can express entropy S to be equal to a function of temperature and volume. We can express entropy S to be equal to the function of temperature and volume. If we do that, we can also express this equation by taking the partial derivative. From our previous videos, we can rewrite this equation as the S is equal to the partial derivative of S all over the partial derivative of T, keeping V constant, the T, this is going to be plus the partial derivative of S all over the partial derivative of V, keeping T constant, dV. This is what we are going to have. We can name this equation to be equation 1. We can call this equation 1. So next, we also know that U, which is internal energy, can be written as a function of temperature and volume. We are going to be expressing this in just the way we express the above change in entropy. So we also know from isochloric process that the partial derivative of U is nothing but Cv dt. So it implies that since the partial derivative of U is equals to Cv, the partial derivative of T, for an isochloric process, that is a constant volume process, we can as well say that Cv, by making Cv the subject of this relation, Cv will be equal to the partial derivative of U all over the partial derivative of T, keeping V constant. Next, we are going to substitute the value of Cv for this in this above equation, that is the U will now be equal to Cv instead of the partial derivative of U over the partial derivative of T, keeping V constant. If we do this, this equation will become the constant dV. We know from our thermodynamic relations from first and second law of thermodynamics that Tds is equals to du plus P dV. We know that Tds is equals to du plus P dV. If we make du the subject of this relation, du will be equal to Tds minus P dV. Du will be equal to Tds minus P dV. So we can substitute the value of du for du in this equation. If we do that, du will be equal to, that is Tds now minus P dV, Tds minus P dV will be equal to Cv dt plus the bracket of the change, that is the partial derivative of U all over the partial derivative of V, keeping T constant, dV. What we are going to do next is that we are going to take minus P dV to the other side of this equation. When we take it to the other side of the equation, the equality sign will become positive. That implies that we are left with T ds. What we are going to have next, this is what we are going to have, whereby we have positive P dV here by taking minus P dV to the other side. Next, we are going to be factoring dV. Since dV and dV are common in these two both terms, we are going to be factoring dV out. This implies that the equation becomes Tds is equals to Cv dt plus the bracket of what we have. So next, we are going to be dividing both sides of the equation through by T. If we do that, we are going to have Tds all over T is equals to Cv dt all over T divided by T, and this term here divided by T. Now from here we know that T can go with T, we will be left with Tds. This equation will now become ds equal to Cv dt all over T plus, now if we take the inverse of this, we will be having 1 all over 2 multiplying this bracket. If we have that, we can say 1 is going to be plus 1 all over t into the bracket of the partial derivative of u all over the partial derivative by the partial derivative of v, keeping t constant, plus p v. So this is what we have. So this is what we have by dividing through by t. So next, we can call this equation to be equation 2, say equation 2. Now we are going to be comparing equation 2 and equation 1. That is, we are going to be comparing the coefficients of the t in equation 2 with the coefficients of the t in equation 1. If we do that, Cv, it will be Cv all over t equal the coefficient of the t in equation 1, which is the partial derivative of s all over the partial derivative of t, keeping v constant. If we multiply both sides of this equation by t, we are going to be having Cv to be equal to t into the partial derivative of s all over the partial derivative of t, keeping v constant. Now, we are going to be differentiating this equation with respect to t. We are to respect to v rather. If we differentiate this equation with respect to the Cv all over the partial derivative of v to be equal to t into d square s all over the partial derivative of t multiplied by the partial derivative of v, keeping v constant. This is what we'll be having. Now, from Maxwell equation, we know that the partial derivative of s from Maxwell equation all over the partial. So this is what we have from Maxwell equation. We say Maxwell have from Maxwell equation. Now we are going to be differentiating this Maxwell equation with respect to t. If we differentiate this equation, the partial derivative all squared of s, that we're going to have the partial derivative all squared of s all over the partial derivative of t multiplied by the partial derivative of v to be equal to the partial derivative all squared of p all over the partial derivative of t all squared, keeping v constant here. So this is what we are having. So next, we are going to be comparing both equations and substituting. So next, we can call this, since we have this to be our equation 2, we can say this to be our equation 3, and also name this equation 4. This is our equation 3 and equation 4. So from here we can see that the partial derivative all square of s all over the partial derivative of t, the partial derivative of v, keeping v constant, is equal to this in this equation. So next we are going to be substituting the value for this. So this equation now will become the partial derivative of Cv. We are going to have the partial derivative of Cv all over the partial derivative of v to be equal to this. But we are having t there, so it will be equal to t into the partial derivative of p square our partial derivative all over the t squared, keeping v constant. This is what we are going to be having. So we know that for an ideal gas, or for a perfect gas rather, we are told that PV is equal to RT from our question. So if PV is equal to RT, we can make P the subject of this relation. If we do that, it implies that P is equal to RT all over V. P is equal to RT all over V. So we can differentiate this equation with respect to t. We can differentiate this equation. We are going to have the partial derivative of p all over the partial derivative of t to be equal to r all over v. To be equal to r over v, we can differentiate this equation again with respect to t. If we do that, we are going to have the partial derivative of p having squared here all over the partial derivative of t all squared to be equal to 0. This is what we are going to have. But don't forget, when we are differentiating, we are going to be keeping v, which is our volume, constant. So this is what we have is the partial derivative all square of p all over the partial derivative of t squared, keeping v constant, to be equal to 0. So next, we are going to be substituting the value of the partial derivative all square of p all over the partial derivative of t all squared, keeping v, which is equal to 0 in this equation. It implies that for this, we are going to be substituting 0. This equation will now become the partial derivative of Cv all over the partial derivative of v to be equal to t into 0, because we substitute the value of this, which is 0, for this in this equation. It implies that the partial derivative of Cv all over the partial derivative of v, this is what we have, is equal to 0. So now you can see from this equation that for a perfect gas obeying PV is equal to RT, we are asked to show that CV and Cp are independent of pressure. From here you can see that the partial derivative of Cv over the partial derivative of V is independent, is equal to 0, that is, it's independent of pressure. So next, we are going to be showing that Cp also is independent of pressure. For us to do that, we know that Cp is equal to T into the partial derivative of S all over the partial derivative of T, keeping V constant. We know that Cp is equal to T into the partial derivative of S all over the T, keeping V constant. Now, we are going to differentiate this equation with respect to P. We are dealing with constant pressure here, so P is going to be kept constant. So we are going to differentiate this equation with respect to P. If we differentiate this, we have the partial derivative of Cp all over the partial derivative of P to be equal to T into the partial derivative all squared of S all over the partial derivative of T multiplied by the partial derivative of P, keeping P constant. This is what we are going to have. Next, from Maxwell's equation, we know that into the partial derivative of V all over the partial derivative of T, keeping P constant. So next, we are going to be differentiating this Maxwell equation with respect to T. With respect to T, we are going to have the partial derivative of S squared all over the partial derivative of P multiplied by the partial derivative of T, keeping T constant, to be equal to minus T into the partial derivative squared of V all over the partial derivative of T all squared, keeping P constant. This is what we have. Now from here we can see that the partial derivative of S, the partial derivative squared of S all over the partial derivative of T all over the partial derivative of P is equal to what we have here. So it implies that we'll be substituting this for this in this equation. It implies that we are going to have the partial derivative of Cp all over the partial derivative of P to be equal to minus T into, it will be equal to minus T, yes, we are going to be substituting it because it will be equal to T into the partial derivative all squared of V all over the partial derivative of t squared, keeping p constant. So from here we can say that the partial derivative of Cp all over the partial derivative of p is equal to minus t squared into the partial derivative squared of v all over the partial derivative of t squared, keeping p constant. So this is what we have. From our PV relation, we know that PV is equal to RT. We know that PV is equal to RT. And if PV is equal to RT, we can decide to make V the subject of this relation. If we do that, we are going to have V to be equal to RT all over P. We are going to have V to be equal to RT all over this equation with respect to T. If we differentiate this equation with respect to T, we are going to have the V all over the T to be equal to R all over P. It implies that we are going to be keeping P constant here. If we differentiate this equation again with respect to T, we are going to be having this square V all over the T square to be equal to 0. Now from here we can see that this square V all over the T square is equal to 0, keeping P here constant. Now it implies that we can substitute 0 here in this equation. If we do that, the partial derivative of Cp all over the partial derivative of P, partial derivative of Cp all over d of P will be nothing but t squared into 0. 0 multiplied by t squared, it implies that the partial derivative of Cp all over the partial derivative of P will be equal to 0. This is what we have. So from here we can see that Cp is independent of pressure. That is, the partial derivative of Cp all over the partial derivative of P is equals to 0. So we have shown that for a perfect gas, obeying PV is equal to RT, Cv and Cp are independent of pressure. Thank you.